Hello and welcome to a course on exam techniques for Grade 12 Mathematics. Thank you for the opportunity to share knowledge on terms of algebra and how they produce a solution in mathematics. Here, the focus is on how to use the Bodmas rule to simplify various quadratic or exponential expressions into their standard forms. Ultimately, singular values of a mathematical expression are obtained as solutions to a standard form. Now, let us see how all this comes together in a typical exam session. Suppose the problem is to find singular values of a rational quadratic form defined as x squared minus 3x minus 10, as in this slide. To do this, first, note that the expression is already in standard form, and the sign of the middle term is negative. A quadratic equation has at most two factors. In this case, the first factor is x minus 5 because the middle term had a negative sign. The second factor is x plus 2, so that the product of negative 5 and positive 2 can give us negative 10. Which is the constant term of a given quadratic form. Now, the nota bene states that a product of two factors is 0 if and only if either factor is 0. That is, either x minus 5 equals 0 or x plus 2 equals 0, as seen on the slide. Therefore, singular values for x squared minus 3x minus 10 are x equals 5 or x equals negative 2. The next question considers the expression defined as 3x squared minus 6x plus 1. Note that the singular values of this expression are irrational. Hence, a quadratic formula can be used to obtain the solution to the expression. The formula given on the slide can be found at the back of a question paper on the day of the exam. So, to solve for x, identify from the equation a value for a equal to 3, then b equal to negative 6, and then c equal to 1. Then plug these values into the formula as shown on the slide. And then, using a pocket calculator, these formulae is evaluated initially with respect to a positive square root, so that a singular value is 1.82. This same formulae is again evaluated with respect to a negative square root, so then a singular value is now 0.18. Consider next an expression of natural exponential form, defined as base 2 raised by a sum of x and 4 plus base 2 raised by x equal to 8,704. To find singular values of this expression, the first step is to standardize each term. The first term is factorized through the converse of the nota bene as a product of base 2 exponent x and base 2 exponent 4. Prime factors of any constant, such as 8,704, must be confirmed using a pocket calculator. This is followed by simplification through separation of a common factor and the arithmetic of constants, as shown on this slide. The equation is simplified further so that base 2 raised by x equals base 2 raised by 10. Since both sides of this equation have the same base, then their exponents are equal. Therefore, x equals 10. Now consider problems of inequality. To solve such problems, it is necessary to find all intercepts. In particular, x-intercepts are obtained using an approach similar to the first question. That is, assuming an equation instead of an inequality. In this case, x-intercepts are 8 and negative 2, respectively. And then for y-intercept, let x equal 0, so that y intercepts its axis at negative 16. Notice that both the standard form and the y-intercepts are negative. That is, in both cases, the inequality sign is the same as less than or equal to. Since critical points of x are negative 2 and 8, the solution is in the interval defined by negative 2 less than or equal to x, which is also less than or equal to 8. Note that some exponential expressions contain terms such as a square root. Also recall that, as seen on the slide, a square root is like raising a base by an exponent equal to a fraction of 1 over 2. Now, take a square for each term on both sides of the equation to end up with an expression without a fraction in its exponents.
And then simplify so that the equation becomes 9x plus 18 equal 4 minus 4x plus x squared. This standardizes to x squared minus 13x minus 14, with singular values x equal to 14 and x equal to -1.
It is necessary to test if both these singular values are valid. If x equals 14, then the test sum of x and 2 equals 16. Since this is positive, x equals 14 is a valid singular value. If x equals a -1, then the test sum of x and 2 equals 1. Since this is positive, x equals -1 is also a valid singular value.
Now, dealing with simultaneous equations involves singular values for two variables, x and y. In this case, two sides of a rectangle are given in terms of x and y for its length and breadth, respectively. Furthermore, given is its perimeter equal to 24 and area equal to 32.
To solve both x and y, initial steps simplify the perimeter in terms of x and y. First note, the perimeter is twice the sum of length and breadth. In simple terms, the perimeter is expressed as 2 times the sum of y plus x minus 1. Now recall that the perimeter also equals 24, so evenly y plus x equals 13. This simple equation is labeled number 1.
Moving on to the area, it is always a product of length and breadth of a rectangle. In this case, the area is yx plus 2y minus 3x minus 6.
The area also equals 32. So then, the simple equation labeled 2 is defined as yx plus 2y minus 3x equals 38. Next, equation 1 is standardized to obtain an equation labeled number 3 as y equals 13 minus x. Now, substitute equation 3 into equation 1 and then simplify using the BODMAS rule to obtain two factors of a quadratic equation. These factors are x minus 6 and x minus 2, respectively. Then, the singular values of x are x equals 6 and x equals 2. Substitute these into equation 3 such that for x equals 6, y equals 7, and for x equals 2, y equals 11. This last question requires defining a function of x and then obtaining factors of the same function. The goal is to show that at least one factor is 2. In the initial step, the function of x is defined as a difference of two squared terms. The first term is defined as 1 plus x exponent m plus x exponent -n. The second term is defined as 1 minus x exponent m minus x exponent -n. The next step removes a common negative factor on the second term of the function, leaving a subterm of x exponent m plus x exponent -n. Now let k equal this subterm. That is, let k equal x exponent m plus x exponent -n, so that the function of x simplifies to 4k, as shown in this slide. Therefore, as required, the function of x is divisible by 2. The quotient is 2k. I hope you enjoyed my thoughts on exam techniques for mathematics questions on algebra. Please subscribe to our channel, like this video for more likewise, and share it with like-minded friends. See you next time.